rubbed my eyes so much that I was in a parallel universe for a second.
And you know that just went on the video that started. I'll try to chop the beginning off. Okay, so here we go.
That's fine. You can keep it in.
Okay. All right. Entertain generations to come.
Yeah.
Okay, here we go. Classwork 4-3. If we were in an in-class setting, this would be a lot of fun, but we are not in an in-class setting, and we also don't have an hour and a half. We only have an hour. So unfortunately, I need to just throw at you some answers and move from there. And as we look at them, I want to talk to you about why this is presented to you. What is so valuable about this? So we're starting with comparing x squared, and x cubed when x is 10. Let's say it'll feel more emotional if you pretend it's you. You and two friends go out to the mall. Well, pretend it's not COVID time. And you have enough money to buy lunch. You have a friend who can buy a nice pair of jeans, and you have to wait on the friend with $1,000 of pocket change, and your friends don't share with you, so you just have to deal with it. So that doesn't feel good, does it? But then if I move up, it gets worse. Let's say you're X and you have $100, and you have a neighbor, X squared, who has $10,000. And then you have another neighbor who has $1 million to your 100. So you can go get a nice pair of jeans, but one of your neighbors can get a used car. Another one can actually buy a home in Encinitas. That gap is much more profound than the gap when X was 10. And that's the most valuable thing for you to see here, is the socioeconomic gap between you and your friends when X was only 10 was just frustrating, but not, oh, people do. Believe me, people do buy jeans for $100. In fact, that's a low price for some. Anyway, you don't feel, yeah. When your x is 10 and you look at x squared and x cubed, you're kind of still within the same social circle. You can be still within the same social circle. You're annoyed though. But when you're dealing with, you have $100 and you're dealing with someone else who has 10,000, someone else who has 1 million, and they're not sharing any money with you. You can't go on vacation with them. You can't do a lot of things. If you think of this as a socioeconomic gap, what you experience when you're 10 is nothing compared to what you experience at 100. And then if you keep going up, it gets ridiculous. Just hitting 1,000, then you're looking at, you have a friend with 1 million and another one with 1 billion. Now, I looked up what can you buy for $1 billion, and apparently you can buy a Major League Baseball team with a low ranking for $1 billion. But then it gets even worse as it goes up. You finally are like the master of $10,000. You can buy a used car, baby. Woo! But X squared has $100 million. So they can buy any car they want, plus a nice home. How about an additional vacation home? You are not you in the same standing. And then the person with $1 trillion, I pretty much would say they can buy a country or political power over an entire nation of people. What you can do with buying a used car compared to being able to buy people is insane. And if you just compare even X, yeah.
With that much money, you could just, buy several people and make them fight to death in a gladiatorial arena without getting.
Okay, we're recording, so let's not go there right now, even though we know that has happened and unfortunately does happen.
Wait, it does?
Stuff like, oh my gosh, stuff like that happens. And it's sad. Anyway, even if you are comparing x squared and x cubed, imagine the difference between those two alone. Can you see that their socioeconomic gap is first like, meh? Gosh, your comments. And so 100 to $1,000, not too big of a deal, but 10,000 to $1 million is a really big deal. If you're a millionaire versus a billionaire, totally different status. And then you can reach 100 million, but your friend over there with $1 trillion can pretty much own you even. They can affect the politics that affect you. So you want to understand how important it is to be a higher degree when you grow. So what you want to understand about polynomials is when the variable x gets exceptionally large, the highest degree term, the entire leading term, takes control of where that polynomial goes. Because if you've got $1 trillion and someone says, I'll donate 100 million to your cause, they're like, keep it. It doesn't affect them. So you want to understand that when you are looking at, let me go back over here. When you are looking at polynomials like these, and you're thinking, what happens when I plug a really large x in? The x cubed term, if you are a large enough number, is so much larger than what you can possibly obtain from x squared that it doesn't matter what number you multiply x squared by, it will become irrelevant to the x cubed. If you are heading to infinity, that socioeconomic gap that I was talking through gets worse as you go and continues to get worse. So this is leading you to polynomial end behavior, which, by the way, is a fun time where you get to do disco, woo, and dance moves. Yeah, it's going to be fun. So the most important thing I want you to write down in your notes starts right here. Right here. Make sure you have this written down. I will forgive you if you don't do the part above it and turn it in. Okay? So, starting right here. Very important to understand that highest degree term, called the leading term, takes control of the polynomial's y value. And before we get into some notation, I want to make sure you understand that when I write x arrow positive infinity, that's saying x is heading to positive infinity. What does that mean? It means when you're on the right end of the graph. And when I talk about x heading to negative infinity, that means you're dealing with the left end of the graph. Now, f of x represents the y value, and y has up and down directions. So when you see f of x heading to positive infinity, what that's saying is that the graph is heading up. If f of x is heading to negative infinity, that says the graph is heading down. And you will be expected to use these 4 notations. So here we go. Whoop, don't show the answers. Do you need me to go back to what was just there in the answers? Actually, you know what? It's on, I have it posted. Yes, posted. I almost said pasted. All right, here we go. What is the leading term of polynomial number 1? What is the leading term? Five x cubed. What is, and just to clarify, what's the leading coefficient? 5, good. Okay. What is the leading term of polynomial number 2? Was everyone getting that? What is the leading term of the third polynomial? What? Oh, got it. Good, thank you. And last, the fourth polynomial, what is its leading term? And make sure that you understand it's not because it's the one to the left. These are polynomials written in standard form. It's the one who has the highest degree, the highest exponent. Okay, now, I want to help you save time because you don't want to sit here and do too much arithmetic. If x is equal to 100, what is x cubed? If x is equal to 100, what is x cubed? I'm going to write 3 sets of 2 zeros. And so the leading term, if it is 5x cubed, when x is 100, the leading term is 5 multiplied by that, so it's 5 million. And again, I have an x cubed. So if I just look at plugging 100 in, and I get, and I cube it, I get 1 million. But then I multiply it by -2, so I have -2 million. What number do I get if I plug 100 into x to the 4th power? I just wrote 4 sets of 2 zeros. So we are now looking at 100 million, and I multiply it by 3, and I have 300 million. Very good. And then lastly, what is the very last one when I plug 0 or plug 100 into x? There we go. Let's see, what is that? 1,000, million, billion, trillion. Yep, very good. So -8 trillion. Now, I didn't want to have you deal with too much arithmetic, but I want you to recognize that if you plugged 100 into all of these lesser degree terms, comparatively, it wouldn't be that big when you're looking at 5 million. And that's going to happen for all of these. if we had more time, I would like to actually have us look more at these numbers so that you understand a bit more why this happens the way it does. But here we go. What I'm trying to get you to see here is that 100 is on its way to infinity, but I didn't want to go too crazy on making you do calculations. If we kept plugging in larger numbers into x, because 100 isn't very big compared to how big numbers can be. So what you want to see is these lesser degree terms that are adding or subtracting will not affect the answer that goes here. And I wanted you to write out the value of the leading term at a large x to see that if x is heading to that positive infinity, it looks like f of x is heading to positive infinity as well. Yeah, make sure you watch the video if your Wi-Fi keeps going out. Now, if you look at this second one with negative 2 million, what do you think is the correct response for as x approaches positive infinity, f of x approaches? Yes, negative infinity. And what do you think about the next one? As you look at this one. Positive infinity and then negative infinity. Now, what I'm hoping for you to get out of that is a particular conclusion. X approaching positive infinity is the right end of the graph. If I get I got positive infinity out. So basically this is saying the right end of the graph heads up for these two polynomials. And then it says that it heads down for the other two polynomials. And if you think about how you got a positive versus a negative number, what do you think determines whether the right end of your graph goes up or down? Who do you think tells you whether your right end goes up or down? And the sign in front is the sign of vocabulary word. The leading coefficient, you got it. So the sign of the leading coefficient determines if the right end of the graph heads up or down. So if the leading coefficient is a positive number, as x approaches positive infinity, f of x approaches positive infinity. If the leading coefficient is a negative number, then when x approaches positive infinity, f of x approaches negative infinity. All right. You know, maybe I should show you a little bit of what polynomial graphs look like, just so that you can at least have some reference to this before I keep going. So I'm just going to throw out some lovely polynomials. Y equals x to the fourth minus 3. I'm just throwing out random stuff. Okay, anyway, I just put in a few things. So this is an example of a polynomial function. When I talk about the right end, I'm referring to this right here is heading up. Right now I have a positive leading coefficient on x to the fourth. Are you ready to see that change? Negative leading coefficient Now the right end is heading down, and it definitely made more changes than just that. But as far as figuring out whether the right end of your graph heads up or heads down, and I believe from the way you see me, this is your right, correct? This is right to you? Okay. So hold up your right arm. Hold up your right arm. Everyone. This means you have a positive leading coefficient. Now, point your right arm down. That means you have a negative leading coefficient for your polynomial. And let me just do this so that you see a little bit more of the friendly little polynomial thing. How is x always going? Actually, the prompt is x going to positive infinity. This is saying, right now this is saying if x is heading to positive infinity. So it's saying if you look at the right side, what's going on. So it's not that x is going to positive infinity, it's just saying when this does happen, this is what y does. All right, now I'm going to make you do the same thing. So let's save some time. I even said from above table for the columns that you do not need to bother refiguring out. So you're going to just grab what you have up there. We've got 5x cubed, negative 2x cubed, 3x to the fourth, negative 8x to the sixth. And then from above, leading term when x is equal to 100. Go ahead and just write 5 million. I mean, that's just getting ridiculous. Negative 2 million. And then 300 million. Negative 8. That was, wait. What? That was negative 8 trillion, correct? Tell me if I'm wrong, because I'm trying to like visually see my groups of zeros. And all right. Also from the above table, as x approaches positive infinity, f of x approaches, and we already figured out positive infinity. So right now I'm copying this down, negative infinity, positive infinity, and negative infinity. All right. Now for the new information. What is the leading term if x is negative 100 instead of positive 100? Can you see that for the first one, if you cube negative 100, you're going to get negative a million instead of positive a million, and the leading term has a value of negative 5 million. For the next polynomial with negative 2x cubed, if I plug negative 100 into my x cubed, I will get negative 1 million, and then I will multiply negative 1 million by negative 2. And that means I'm going to have positive 2 million. For the next polynomial, here's my leading term. If I plug negative 100 into the x to the fourth, I'm going to get exactly what I got when I plugged in positive infinity. And then the last one, do you see that if you plug negative 100 in x to the sixth, that's going to give you nothing different than when you plug positive 100 into x to the sixth? Now I have a next question for you. Polynomial number 1. Is its degree an even number or an odd number? Correct, odd. Polynomial number 2. Is that an even degree or an odd degree? Odd degree. Third polynomial. Yep, you got it. And then even degrees on those. And do you see that the reason that I brought out this question is because when you have an odd degree polynomial, the right end and the left end go in opposite directions. But when your polynomial is even degree, then you don't get anything essentially different on the right end as you do the left end. So you're getting that the ends go in the same direction if you are dealing with an even degree. So now we're going to base this column on what we got with these leading terms. Now I'm saying as x approaches negative infinity, that means as I head to the left, I want to know, does the graph head up or down? If I'm at negative 5 million when x is negative 100, do you feel good that it's heading to negative infinity? And then the next one, it looks like it's heading to a positive infinity. Next one looks like positive infinity. And the next one looks like negative infinity. And a conclusion. If the degree of the polynomial is odd, then the left end goes in the direction as the right end. What do you think means?
Opposite.
Woo! Opposite. If the degree of the polynomial is even, then the left end goes in the direction as the right end. Same. And then I've got a nice little chart to conclude. So it starts with everything that is to the left of this line. You know what? Let me draw the line in. Everything to the left of this line is under the idea that you have a positive leading coefficient. Everything on the right side is based on you have a negative leading coefficient. So I'm going to start with, if you have a positive leading coefficient, when x approaches positive infinity, f of x approaches and you guys are probably getting positive infinity. If you have a negative leading coefficient, then when x heads to positive infinity, the right end of the graph, f of x approaches, and I'm hoping you see negative infinity. Now, if you are under the positive leading coefficient, and you additionally know that you have an even degree, then what is the left end of the graph doing? And I want to see it in chat. If you have a positive leading coefficient and your polynomial is an even degree, is the left end going up or down? Correct. we are heading to positive infinity, meaning the left end is heading up. So everybody, score! Let me see that. Score! Yeah. You just experienced a polynomial with a positive leading coefficient and an even degree. Now, still positive leading coefficient, but if the degree is odd, then does the left end head up or down?
Down.
Thank you. So negative infinity. Now, everybody, it's time to dance disco style. Woo! Show me your polynomial with a positive leading coefficient and an odd degree. Yeah. And I'm trying to mirror because I believe this is your right. Okay. So what does that mean in picture? And I'm just going to draw some crazy thing for fun. That means if you are a positive leading coefficient and an even degree, the two ends, the right and the left end, head up. Now, what goes on in the middle? Craziness. I don't know what. Maybe it goes tra-la-la-la-la-la-la. Maybe not quite that. That's a seriously high degree polynomial that can do that, which you're not going to deal with. The primary thing you want to be the primary thing that you want to understand is that these two things together means this is your end behavior. And then positive leading coefficient, odd degree, tells you this is happening. And then whatever goes on in the middle goes on in the middle. Whee! Maybe it's that, maybe it's something else. But again, I want to emphasize that it's this end behavior of these little blue arrows. Of course, if you're colorblind, you can't tell they're blue, but you can see those arrows. All right, now, if you have a negative leading coefficient and your degree is even, what's the left end going to do? I'm waiting. If you have a negative leading coefficient, your right end is heading down, and an even degree means the other end follows down, and it's going to be sad. Now, if your right end is heading down and you have an odd degree, what is your left end doing? Heading up to positive infinity. So the visual on that is, with the negative leading coefficient, the negative leading coefficient causes the right end to be heading down. If I am an even degree, then I have to come back and head down on the left end. If I am an odd degree, then whatever happens through here, I have to eventually head up on the other end. Okay, I was afraid of this. I'm going to postpone your quiz until Monday. All the quizzes are pushed because I've got to finish this. We'll push quizzes.
You guys, there was no quiz today.
Hey. Okay. Now, that was end behavior. Then there's middle behavior. You need to know that a polynomial is pretty and smooth. It does not have, let me head over to the answers because I have 5 minutes left to try and get through the rest of this. So right here, I am showing that you have a nice smooth curve, but it doesn't have these sharp points like this. And I want to point out that this is degree 2 and higher. If you are degree 2 and higher, you are curvy. You don't have a bunch of straight lines going on. So you want to make sure that when you graph polynomials that are degree 2 or higher, that they look like they're curvy. They don't look like teeth. Okay? You get what I'm saying about that?
So you're saying it's funky.
All right. Now, I've got some examples of you, or some examples for you of polynomial graphs by degree. If you are degree 0, then you are, say, 5, the number. And that means you have a positive leading coefficient if you're 5. And does it make sense that if you graph y equals 5, you're getting a flat line? But if it's negative 5, you still have a flat line. It's just underneath the x-axis. That's all. If you have a degree 1 polynomial, it's a linear function. And basically, it's a line with a positive slope. If it's a positive leading coefficient, and a negative slope if it has a negative leading coefficient. And you might recall with parabolas, do you remember it goes up when the number in front of x squared is positive and down when the number in front of x squared is negative? And now we move that up a degree or 3 degrees. So make sure that you understand these right here. A 3rd degree polynomial can only get so crazy. The higher degree, the more action might take place in the middle. But that doesn't mean there is action. Some are high degree and very boring. So some examples of 3rd degree polynomials with a positive leading coefficient and a negative leading coefficient. Some degree 4s with a positive leading coefficient and a negative leading coefficient. And you can see that they do a little bit more. A 5th degree positive leading coefficient, negative leading coefficient. Right now, you're getting used to graphs and end behavior. I'm down to 1 minute left. This means for your homework over the weekend, you're going to want to use these to help you do your homework. I'm going to keep talking. You cannot go yet, but when it hits 1:50, I can't stop you from going. I'm going to continue recording for just a little bit longer. When you look at the graph of number 1, can you see that it is an odd degree and a positive leading coefficient? And that means that these are your answers to end behavior. For number 2, can you see that it's an odd degree because it's doing a disco dance? And then the right end is heading up. That means the leading coefficient is positive. And then the formal notation you will be expected to use is right here. And hopefully you can see that this one is also an odd degree polynomial. This one is an even degree polynomial. Both of these have right ends heading downward. That means they have negative leading coefficients. And then this is the formal way that you will be expected to write that end behavior. And I will post this video so that you can finish writing. I was afraid I wasn't going to get through everything here. Here, can you see it's an odd degree with a positive leading coefficient? This one, the two ends go the same direction, so it's an even degree. The right end heads down, negative leading coefficient. And then lastly, I have some equations. Yes, you're allowed to leave. With these equations, number 7 is a degree 1 polynomial that makes it odd. Its leading coefficient is positive 2, and those two things together determine the end behavior. Number 8, your largest exponent is a 4. That makes it an even degree polynomial. The coefficient of x to the 4th is positive 1. So that means your leading coefficient is positive, and those two together determine the end behavior. Lastly, I have an odd exponent for my largest exponent. That makes it an odd degree. The coefficient for that x cubed is negative 2, and that determines the end behavior. So that was a huge bunch of stuff thrown at you, but you've got the weekend to process it.